In this video, we're going to learn how we can define and set up neural networks using a package called Torch. We've talked about neural networks as being composed of layers, and you can see an image representing that here. So we have these four different layers, each represented by a different color, and each layer contains nodes. Right? So we can think of each input variable as its own node. Right? We have three of those here. And then in this second layer, which is called hidden layer one, right, we have four nodes. Each of the input variables gets supplied to each of these nodes in the next layer. And then each of these nodes, right, creates an output, a prediction, and that prediction gets supplied on to each of the nodes in the next layer, right, and so forth, until we get to the final layer called the output layer, which just takes in each of the predictions of the preceding hidden layer. Now you can think of these nodes in these layers as essentially being simpler models, like a logistic regression or almost a linear regression. We're going to use an application called Torch to build neural networks. This is not an R program in and of itself, but there is an R package which enables us to use it. This package is called Torch, and since in this example we're going to be analyzing image data, we're going to need another package called Torch Vision that has some useful tools for doing that, as well as a package called Luz, which helps us create deep learning models in R. Now, the example we're going to show here is with a data set called MNIST. This is quite a famous data set of images, which for a long time was quite a hard challenge. Before deep learning was invented, researchers used this data set as a way of trying to create better and better models. These days, deep learning is so powerful that the MNIST dataset is not really a challenge for it. So each picture in this dataset contains a single digit handwritten number, 0, 1, 2, 3, etc., all the way through 9. And each of these images is standardized to be the same size, so it's 28 pixels wide and 28 pixels high. So what do we mean by pixels? Well, you may know that an image is made up of pixels, right? If you've ever zoomed in on a computer image really to a really high level of magnification, you might have noticed that it becomes these sort of blocky little colors of, it becomes these blocky little squares of different colors. And so a pixel is essentially a little square that has a single color, right? And if we have images made up of enough of these pixels, then when we zoom out to our human eyes, it will look continuous rather than discrete. Now, the MNIST images are actually in grayscale, which is kind of like black and white, except that it has all the shades of gray in between those two. And you can see an example of that here, right? So this is a picture that has the digit 3 in it, and we can see that these pixels where the color is white have the number 0, and these pixels that are darker have higher numbers, right? So if the pixel is black or almost black, then the numbers can go as high as 255. Shades of gray will be somewhere between 0 and 255. So we can use these numbers as inputs to a model, right? Each pixel is essentially its own variable, its own input variable to the model. So if we have a 28 pixel by 28 pixel image, then we can multiply those two numbers together to get the total number of pixels in each image, which gives us 784 pixels, right? Each one of which will be an input variable to this model. Now, to make our lives simpler, we're going to flatten this two-dimensional grid of pixels into just one long column of numbers, right? So it's almost like converting it into a single row of a data frame. So here's some code that will do this with the torch package, and we're using a function here called mnist_dataset that comes with these packages that can load the mnist data. We tell it what folder we want to use to hold all the files, whether we wish to download the files, which in this case we do. And then finally, we have this transform argument, which is telling Torch how to convert the images into this this one-dimensional vector of numbers. Okay, and we're assigning that all to a variable called train_ds. Now, we previously talked about cross-validation as a way of validating our models without losing a bunch of data. That is still holds in the case of deep learning, but for simplicity here, we are just going to have a fixed validation set for our data. All right, so we're going to use this data subset function to split out the training data set, right, train_ds into two separate variables, right? So images numbers 1 through 10,000 are going to be reserved for the validation data, and then the remaining 50,000 images are going to be assigned to train_ds. Now, the MNIST dataset is relatively small, but in many cases, when you're working with images, you'll have quite large images, and you'll have a lot of them. So we can't hold all of those images in the computer's memory at once. So we need a solution that allows us to access the images for training without accessing all of them at once. And the solution to this is to just improve the model on a small number of images at once, okay, called a batch of images. And so what we do effectively is you could think about it if we had a linear model that we were training with batches, we would take a batch of observations, right, a smaller number of all the observations we had, and we would just improve the slope and intercept of that linear model slightly for that batch of images, right? We wouldn't try to make it as good as possible necessarily on that batch. We would just try and make it ever so slightly better. And then you would go on to the next batch of observations and make another little improvement, right? And so over time, what happens is that you sort of you reach a point where it's hard to make any more improvements, right? You sort of end up sort of just shuffling backwards and forwards around the average. Now in code, what this looks like is that we have to create something called a data loader, okay? And this is going to load batches of images for us from the training data set. Okay, so here we're making a data loader for the training data images as well as for the validation images using this data loader function and assigning the outputs to train_dl and to valid_dl. Now, the key thing here is we're creating a batch size of 32, which means that each batch will hold 32 images. And for the training data loader, we are shuffling up the order that we get those images in so that it will be a little bit random each time we go over the data set. So here's an example of an image from the data. We're using a function, a custom function here called visualize image to plot it as a ggplot graph. And this is just taking one of the images from a batch loaded by the train_dl data loader. Now, label 6 means that this is, in theory, the digit 6 in this image. As you can see, in some of these images, it can be quite hard to actually recognize the images even to the human eye. So we mentioned we had these hidden layers, which contain a number of nodes, and each node is essentially its own little model. And what it does, what each node does, is it takes a linear combination of the inputs, right? So if the inputs of the previous layer's nodes are x1, x2, etc., all the way up to xn, then we essentially have a slope or a coefficient for each one of those plus an intercept, and that gives the output of that node, right? So this is just like a linear model. However, because we want to convert this into sometimes a non-linear output, what we do is we then take the output y of this linear part of the node and we run it through something called an activation function, okay, which is a function that makes it nonlinear. One example of a function you could use would be the sigmoid function, which is the same function we've used in logistic regression, which converts linear model predictions to a number between 0 and 1. So we have to define how many of these hidden layers we want in our model, and we also have to define what type of nonlinear activation function we want after each of these layers. So with the torch package, we're going to use a function called nn_module. We have to specify a name for this model, which is the first argument, and then we also need to provide two more arguments, initialize and forward. So here's an example of what the initialize argument could look like. Right, it's taking a function as the value we're passing to it. Okay, we're defining a function within this function call. Okay, and we don't have to worry too much about the details here, but the highlighted yellow parts are the most important parts because this is defining the layers that we have. Right, remember we said that these MNIST images have 784 pixels, right? So this initial layer needs to take in 784 inputs. Okay, we're creating these layers with the NN linear functions, right? The first argument is the number of inputs. The second number is the number of outputs, right? So here we're saying that there's going to be 256 outputs of this layer, which means that we're going to have 256 nodes in this first hidden layer. Okay. Next up, then we add an activation function. Here we're using something called the ReLU activation. This doesn't need any arguments. And then finally, we have another linear layer. Okay, this takes the 256 outputs, okay, of the previous layer, and it converts them into 10 different values. Okay, these are going to be our predictions, right? Remember, we have 10 numbers. So effectively, we're going to be predicting a score for each of the 10 digits that the image could contain. Okay, and then the way we would make a prediction is we would say, okay, which of these 10 possible outputs is highest? Okay, and then that's the number that we're going to predict as an image, right? So the 6th output in this layer of 10 outputs was the highest. We would predict that it's the 6th digit that's in the image. Now, it's important when you're creating these that the dimensions match. So if you have 784 pixels, but you only wrote 700 here, then you get an error when you tried to run this model. Similarly, if you have two layers, right, then the number of outputs of this layer needs to match the number of inputs of this next layer. Finally, we have this forward argument. This effectively runs the neural network that we set up in the initialize argument. This is what the model will use when it's trying to run the model on a particular image.